When selecting conduit size and type for a feeder run using number 4-3 wire from a service meter to panel, several factors dictate the appropriate choice according to the National Electrical Code. These factors include the number of conductors, the conductor size, and the conduit material. In this specific case, we are dealing with 3 conductors: phase, neutral, and ground of number 4 American wire gauge size, and the conduit material under consideration is polyvinyl chloride Schedule 40, commonly referred to as PVC 40. The National Electrical Code mandates that the conduit size must be sufficient to accommodate the number and size of conductors, taking into account any necessary directing factors. Directing refers to reducing the allowable ampacity of conductors based on factors such as ambient temperature or the number of conductors bundled together. For a 3-conductor number 4 feeder run in PVC 40 conduit, the minimum trace size required is 1 and 1/4 inches. It is crucial to adhere to this minimum size to ensure that the conductors can be properly installed and that heat can dissipate effectively, preventing overheating and potential fire hazards. PVC 40 is an acceptable material for underground conduit installations due to its resistance to corrosion and good impact strength. When installed underground, the conduit must be buried at a depth of at least 18 inches below the surface. This depth provides protection from physical damage that could be caused by digging, landscaping, or other activities. Furthermore, the conduit must be protected from mechanical damage by using a slab, trench cover, or other approved method. This additional protection ensures the long-term integrity of the conduit and the conductors it contains. In summary, based on the information provided, PVC 41 and 1/4 inch conduit would meet the National Electrical Code requirements for a feeder run with number 4-3 wire from the service meter to the panel, provided that the conduit is buried at an appropriate depth of at least 18 inches and protected from mechanical damage. Always consult the latest edition of the National Electrical Code and local electrical codes for specific requirements and to ensure compliance. When running electrical conduit underground, several factors must be considered to ensure a safe and code-compliant installation. These considerations extend beyond simply choosing the correct size and type of conduit, and include aspects such as burial depth, protection from physical damage, proper installation techniques, and adherence to local regulations. Firstly, burial depth is a critical factor in underground conduit installations. The National Electrical Code specifies minimum burial depths for different types of conduits and wiring methods based on factors such as voltage level, location type, and presence of vehicular traffic. For PVC conduit, a common choice for residential and light commercial applications, a minimum burial depth of 18 inches is typically required. This depth provides adequate protection from physical damage caused by digging, landscaping, or other activities. However, it is essential to consult local codes and regulations, as they may specify more stringent requirements depending on the specific location and application. Secondly, protection from physical damage is another crucial aspect of underground conduit installations. While burying the conduit at the required depth provides some protection, additional measures may be necessary to safeguard the conduit and its conductors from potential damage. This can be achieved by encasing the conduit in concrete, using a reinforced concrete slab, or installing a trench cover. The choice of protection method will depend on factors such as the severity of potential physical damage, the type of soil, and local code requirements. Thirdly, proper installation techniques are essential for ensuring the long-term reliability and safety of underground conduit installations. This includes carefully preparing the trench, ensuring proper alignment and support of the conduit, and using appropriate fittings and connectors. The trench should be dug to the correct depth and width, and the bottom should be free of sharp rocks or other debris that could damage the conduit. The conduit should be properly aligned and supported to prevent sagging or bending, which could compromise its structural integrity. Fittings and connectors should be of the correct type and size, and should be properly tightened to ensure a secure and watertight connection. Fourthly, adherence to local regulations is paramount when installing underground conduit. Local electrical codes and regulations may vary from the National Electrical Code, and may impose additional requirements or restrictions. It is essential to consult with local authorities and obtain the necessary permits before beginning any underground electrical work. This will help ensure that the installation complies with all applicable regulations and is safe for both the public and the environment. Finally, documentation and record keeping are important aspects of underground conduit installations. Accurate records of the location and depth of the conduit, as well as any other relevant information, should be maintained for future reference. This information can be invaluable for maintenance, repairs, and future construction projects. In summary, running electrical conduit underground requires careful planning, attention to detail, and adherence to all applicable codes and regulations. By considering factors such as burial depth, protection from physical damage, proper installation techniques, and local regulations, you can ensure a safe, reliable, and code-compliant installation. Always consult with a qualified electrician or electrical engineer if you have any questions or concerns about underground conduit installations. When sizing conduit for electrical conductors, the National Electrical Code provides specific guidelines and tables to ensure that the conduit is large enough to accommodate the conductors without overcrowding or causing damage. These guidelines take into account factors such as the number of conductors, the size, insulation type, and the type of conduit being used. Firstly, the number of conductors is a primary factor in determining conduit size. The more conductors that are installed in a conduit, the larger the conduit must be to provide adequate space for the conductors and to allow for proper heat dissipation. The National Electrical Code provides tables that specify the maximum number of conductors of a given size and insulation type that can be installed in various sizes of conduit. Secondly, the size of the conductors is another important factor. Larger conductors require more space and therefore necessitate a larger conduit. The National Electrical Code tables mentioned above also take into account the size of the conductors when determining the maximum number of conductors allowed in a given size of conduit. Thirdly, the insulation type of the conductors can also affect conduit sizing. Different insulation types have different thicknesses and heat dissipation characteristics, which can impact the amount of space required in the conduit. The National Electrical Code tables specify the maximum number of conductors for different insulation types, such as THHN, THWN, and XHHW. Fourthly, the type of conduit being used can also influence conduit sizing. Different types of conduit, such as PVC, rigid metal conduit, and electrical metallic tubing, have different internal diameters and fill capacities. The National Electrical Code tables provide separate guidelines for each type of conduit. To determine the correct conduit size for a specific application, follow these steps. Firstly, determine the number and size of conductors that will be installed in the conduit. Secondly, identify the insulation type of the conductors. Thirdly, select the type of conduit that will be used. Fourthly, consult the appropriate National Electrical Code table to determine the maximum number of conductors of the specified size and insulation type that can be installed in the selected type of conduit. Fifthly, compare the number of conductors to be installed with the maximum number allowed by the table. If the number of conductors exceeds the maximum allowed, increase the conduit size until the number of conductors is within the allowed limit. In addition to the National Electrical Code guidelines, it is also important to consider any applicable local codes and regulations. Local codes may impose additional requirements or restrictions on conduit sizing, and it is essential to comply with all applicable regulations. Always consult with a qualified electrician or electrical engineer if you have any questions or concerns about conduit sizing. Overfilling conduits can lead to several problems, including overheating of conductors, difficulty in pulling conductors through the conduit, and damage to the conductors or conduit. It is therefore essential to follow the National Electrical Code guidelines and to select the appropriate conduit size for the application. Understanding the National Electrical Code is paramount when dealing with electrical installations. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines that govern the safe installation of electrical wiring and equipment in the United States. It is updated every 3 years to reflect the latest technological advancements and safety practices. The National Electrical Code covers a wide range of topics, including wiring methods, overcurrent protection, grounding, equipment installation, and special occupancies. It is essential for electricians, electrical contractors, engineers, and inspectors to have a thorough understanding of the National Electrical Code to ensure that electrical installations are safe and code compliant. Firstly, wiring methods are a fundamental aspect of the National Electrical Code. The National Electrical Code specifies the types of wiring methods that are permitted for different applications, such as residential, commercial, and industrial. It also provides detailed requirements for the installation of these wiring methods, including conduit sizing, conductor fill, and support requirements. Secondly, overcurrent protection is another critical area covered by the National Electrical Code. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from excessive current flow, which can cause overheating, fire, and equipment damage. The National Electrical Code specifies the types and ratings of overcurrent protection devices that are required for different circuits and equipment. Thirdly, grounding is essential for electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, which helps to prevent electric shock and equipment damage. The National Electrical Code specifies the requirements for grounding electrodes, grounding conductors, and equipment grounding. Fourthly, equipment installation is also covered extensively by the National Electrical Code. The National Electrical Code provides detailed requirements for the installation of various types of electrical equipment, such as lighting fixtures, receptacles, switches, and appliances. These requirements are designed to ensure that equipment is installed safely and in accordance with manufacturer's instructions. Fifthly, special occupancies such as hazardous locations, healthcare facilities, and swimming pools have unique electrical requirements that are addressed by the National Electrical Code. These requirements are designed to protect people and equipment from electrical hazards in these specialized environments. To effectively navigate the National Electrical Code, it is important to understand its structure and organization. The National Electrical Code is divided into chapters, articles, and sections, each covering a specific topic. It also includes numerous tables and figures that provide detailed information and examples. When using the National Electrical Code, it is important to consult the latest edition and to be aware of any local amendments or interpretations. Local jurisdictions may adopt the National Electrical Code with modifications to address specific local conditions or concerns. It is also important to consult with a qualified electrician or electrical engineer if you have any questions or uncertainties about the National Electrical Code requirements. In addition to the National Electrical Code, there are other relevant standards and regulations that may apply to electrical installations, such as the National Electrical Safety Code, the Occupational Safety and Health Administration regulations, and state and local building codes. It is important to be aware of all applicable requirements and to comply with them to ensure a safe and code-compliant installation. Understanding the relationship between wire gauge and ampacity is crucial for safe and efficient electrical wiring. Wire gauge refers to the physical size of a wire, while ampacity refers to the maximum amount of electrical current that a wire can safely carry. The National Electrical Code provides tables that specify the ampacity of different wire gauges based on factors such as the type of insulation, the ambient temperature, and the number of conductors in a raceway or cable. Firstly, wire gauge is typically expressed using the American wire gauge system, where smaller numbers indicate larger wires. For example, a number 12 American wire gauge wire is larger than a number 14 American wire gauge wire. Larger wires have a lower resistance and can therefore carry more current without overheating. Secondly, ampacity is expressed in amps and represents the maximum current that a wire can carry continuously under specific conditions without exceeding its temperature rating. The ampacity of a wire is affected by factors such as the type of insulation, the ambient temperature, and the number of conductors in a raceway or cable. Thirdly, the type of insulation affects the ampacity of a wire because different insulation materials have different temperature ratings. Wires with high temperature ratings can carry more current without overheating. Common insulation types include THHN, THWN, and XHHW. Fourthly, the ambient temperature affects the ampacity of a wire because higher temperatures reduce the wire's ability to dissipate heat. The National Electrical Code provides directing factors that must be applied to the ampacity of wires when they are installed in high-temperature environments. Fifthly, the number of conductors in a raceway or cable affects the ampacity of a wire because multiple conductors generate more heat than a single conductor. The National Electrical Code provides directing factors that must be applied to the ampacity of wires when they are installed in raceways or cables with multiple conductors. To determine the appropriate wire gauge for a specific application, follow these steps. Firstly, calculate the expected load current for the circuit. This is the amount of current that the circuit is expected to carry under normal operating conditions. Secondly, select a wire gauge that has an ampacity equal to or greater than the expected load current. Refer to the National Electrical Code tables to determine the ampacity of different wire gauges based on the insulation type, ambient temperature, and number of conductors in a raceway or cable. Thirdly, apply any necessary directing factors for ambient temperature or number of conductors. If the derated ampacity of the selected wire gauge is less than the expected load current, increase the wire gauge until the derated ampacity is sufficient. It is important to note that the National Electrical Code also specifies minimum wire gauge requirements for certain applications such as branch circuits and feeders. These minimum requirements must be followed regardless of the expected load current. Overloading wires can lead to overheating, insulation damage, and potentially fire. It is therefore essential to select the appropriate wire gauge for the application and to follow all applicable National Electrical Code requirements. Understanding the relationship between voltage drop and wire size is crucial for ensuring efficient and reliable electrical power distribution. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction, reduce lighting brightness, and increase energy consumption. Firstly, voltage drop is directly proportional to the length of the conductor and the current flowing through it. Longer conductors and higher currents result in greater voltage drop. Secondly, voltage drop is inversely proportional to the cross-sectional area of the conductor. Larger conductors have a lower resistance and therefore result in less voltage drop. Thirdly, the National Electrical Code recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. This ensures that equipment receives adequate voltage and operates efficiently. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by circular miles, where K is the direct current constant, which represents the resistance of 1 circular millifoot of copper conductor. I is the current in amps, D is the one-way distance in feet, and circular mils is the cross-sectional area of the conductor in circular mils. To determine the appropriate wire size to limit voltage drop to an acceptable level, follow these steps. Firstly, determine the expected load current for the circuit. Secondly, determine the length of the conductor run. Thirdly, select a wire size and calculate the voltage drop using the formula above. Fourthly, compare the calculated voltage drop to the National Electrical Code recommended limits. If the voltage drop exceeds the limits, increase the wire size and recalculate the voltage drop until it is within the acceptable range. In addition to using the formula, there are also voltage drop calculators available online and in electrical design software. These calculators can simplify the process of determining the appropriate wire size for a given application. It is important to consider voltage drop when designing electrical circuits, especially for long runs or high current applications. Selecting the appropriate wire size can ensure that equipment receives adequate voltage and operates efficiently, preventing malfunctions and reducing energy consumption. Always consult with a qualified electrician or electrical engineer if you have any questions or concerns about voltage drop and wire sizing. When selecting PVC conduit for electrical installations, it's important to understand the different types and schedules available. PVC conduit offers several advantages including resistance to corrosion, lightweight construction, and ease of installation. However, it's crucial to choose the correct type and schedule to ensure that it meets the specific requirements of the application. Firstly, PVC conduit is available in several different types, including Schedule 40, Schedule 80, and electrical non-metallic tubing. Schedule 40 PVC conduit is the most common type and is suitable for a wide range of applications, including underground installations and general-purpose wiring. Secondly, Schedule 80 PVC conduit is thicker and stronger than Schedule 40 and is typically used in applications where greater physical protection is required, such as areas subject to impact or heavy loads. Thirdly, electrical non-metallic tubing is a flexible type of PVC conduit that is often used for concealed wiring in walls and ceilings. It is not suitable for underground installations or exposed locations. Fourthly, the schedule number of PVC conduit refers to the wall thickness of the conduit. Higher schedule numbers indicate thicker walls and greater strength. Schedule 40 and Schedule 80 are the most common schedules, but other schedules are also available for specialized applications. When selecting PVC conduit, consider the following factors. Firstly, the location of the installation is a critical factor. Underground installations require conduit that is resistant to moisture and corrosion, while exposed locations require conduit that is resistant to sunlight and physical damage. Secondly, the type of wiring being installed is also important. Different types of wiring have different requirements for conduit size and support. Thirdly, the local electrical codes and regulations must be followed. Local codes may specify the types of conduit that are permitted for certain applications. Fourthly, the ambient temperature of the installation environment should be considered. PVC conduit can become brittle at low temperatures and may require special precautions in cold climates. To install PVC conduit, follow these steps. Firstly, measure and cut the conduit to the desired length using a PVC cutter or saw. Secondly, deburr the cut ends of the conduit to remove any sharp edges. Thirdly, apply PVC cement to the inside of the fitting and the outside of the conduit. Fourthly, insert the conduit into the fitting and twist slightly to ensure a good bond. Fifthly, allow the cement to cure according to the manufacturer's instructions before handling the conduit. PVC conduit must be supported at regular intervals to prevent sagging and damage. The National Electrical Code specifies the maximum spacing between supports for different sizes of PVC conduit. Always consult with a qualified electrician or electrical engineer if you have any questions or concerns about selecting or installing PVC conduit. Understanding grounding requirements is crucial for ensuring electrical safety and preventing electric shock. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip over current protection devices and energize the circuit in the event of a fault. Firstly, grounding electrodes are used to connect the electrical system to the earth. Common grounding electrodes include metal underground water pipes, ground rods, and concrete encased electrodes. Secondly, the National Electrical Code specifies the requirements for grounding electrode systems, including the size and type of grounding electrodes, the bonding of grounding electrodes, and the connection to the neutral conductor. Thirdly, grounding conductors are used to connect equipment and enclosures to the grounding electrode system. Grounding conductors must be sized according to the National Electrical Code tables based on the size of the overcurrent protection device. Fourthly, equipment grounding is the process of connecting non-current carrying metal parts of equipment to the grounding electrode system. This helps to prevent electric shock if a fault occurs within the equipment. Fifthly, bonding is the process of connecting different metal parts of the electrical system together to create a low impedance path for fault current. Bonding is essential for preventing voltage differences between metal parts, which can cause electric shock. To ensure proper grounding, follow these steps. Firstly, install a grounding electrode system that meets the requirements of the National Electrical Code. Secondly, connect all equipment and enclosures to the grounding electrode system using grounding conductors of the appropriate size. Thirdly, bond all metal parts of the electrical system together to create a low impedance path for fault current. Fourthly, test the grounding system to ensure that it is functioning properly. Grounding is essential for electrical safety and should be performed by a qualified electrician. Always consult with a qualified electrician or electrical engineer if you have any questions or concerns about grounding requirements.